Hello everyone. In this video, we are going to talk briefly about the strain measurement. So if you remember when I talked about the tensile test and I said you're going to plot this stress versus a strain, the question is how do you measure a stress and a strain, right? So we can have such plot. So the answer is for stress, you can have basically stress comes from the forces. So if you can measure force, and there are lots of different ways to measure forces, force sensors, then that's this axis, and this one is basically coming from changing the length. So if you can measure changing the length, that's all you need to measure. Okay, and actually many times they only measure force and displacement, and then when you want to plot, then you divide by those numbers by A and L. But what you need to measure is displacement, the change in the length of the material. Now, there are different ways to do it. All you need is to change the length, relate that change in the length to something else that you can measure, like a voltage. And so the device is basically a transducer. These different, what we call strain gauges, they are different transducers which will convert one form of physical entity, which is changing the length, to a voltage. So the most common ones, the cheapest and the most common ones, are electrical resistance strain gauges. So here, the change in the length corresponds to change in resistance. And if you know the resistance of any material, that's the special resistance, right? And then times length divided by the cross section. So if you make the length longer, you're making the resistance larger. And for that reason, and it's a linear relation, which is the best kind of format, because if the relation is a one-to-one linear, it's the easiest way to calibrate your gauge. So typically, the most common one is also this one called foil strain gauges. So you have typically a thin metal foil pattern, something like that, and it is attached to a backing material, and then you use some adhesive to attach it on the surface of the part you want to measure its strain. And we're going to talk more about this at the bottom of this presentation. You see that I'm going to talk a little bit more about it, but basically, you're going to attach it with an adhesive to the part, to the specimen. You see this dog bone here that you want to measure. And these, they were invented in 1938. So they have been around a little bit short of a century. And they have been working very well. Okay, so we still use them today. And the essence is changing electrical resistance. That's all it is. Typically, the way we measure the change in the resistance is using a Wheatstone bridge or Wheatstone bridge, whatever you want to call it. And we're going to talk about that, okay? But this is the portion of the material that the length of it is going to change due to tension or compression. So it's going to get longer or shorter. And then there are these two terminals for the voltage to pass through. So this is the most common one. Now, there are lots of formats of this, because this one can only be a stretch in this direction or shrink in this direction. Basically, it can only measure this kind of strain. So if this is the x-axis, all it can measure is a strain in the x-axis. But if your material has a strain in the other axis too, you want to change this orientation of this pattern to something like in this direction, so it can also measure epsilon yy. So you see some strain gauges, they have two different patterns on them. So there is one for X and there is one for Y. So these guys can measure both of these strains. And then there are some that are used for shear strain gauges, so they can measure tau. And if you look at them, their angles are at 45-degree angle to measure the shear strain. And again, they can measure in one or two directions. And a group of them is called a rosette strain gauge. I don't want to get into that much of detail of it, but basically, depending on the direction of this pattern, you are able to measure one or two or several directions for strain, and it could be normal strain or could be shear strain. Okay, so this is the most common one. There are some that use semiconductors, They are way more expensive and fragile, but they are way more sensitive, and we're going to talk about that. So these are semiconductor systems as opposed to just a simple metal foil. Then we get to the ones that are my favorite ones, the optical ones. And there is one category called fiber Bragg grating or FBGs. And the other one that I like really, because my background is a little bit computer vision, is this one called digital image correlation or DIC. I really like them. So they are camera systems like this, and they are very sensitive. And the best thing about them is if you have this specimen, it can plot literally for you strain at any point in any direction. So if you look at this one, when you look at that, what you can do is strain in one or two directions, and it is only at the location that you're attaching to. So right now, the only location I can get the strain for is this location here where it is attached. If I want to strain here or here, it changes with the X. I cannot. I have to attach another one, and that is not possible. But with this one, it is very possible because it considers a bunch of different points on this specimen, and then it tracks the location of those points. You probably need to put some markers here, and it looks at the displacement of those points. It tracks them between the beginning and the end of, or it can even give you a real-time tracking. And based on how much they moved in any direction, and it can give you basically the strain in the entire material in different directions. So these are really amazing. There is no contact needed. They are not fragile. You don't need to attach. You don't need electric circuits. They are really, really amazing by analyzing images, but they are, of course, very expensive. Okay, so this is my favorite type of strain measurement. There are the ones that are mechanical ones, and the most common ones are these guys called extensometers. So these are literally you connect the mechanical device extensometer to the portion that you want to see how much it is going to change its length, the elongation of it. And mechanically, you can measure by these rigid attachments, you can measure how much this guy is going to change this portion and then get some kind of average value for that region. Again, you see the limitation, right? It's in one direction and it is an average for an entire region. Okay, but they are typically used most of the time in civil engineering and in cases that we only want like a single number. Okay, like in concrete structures, stuff like that, we can use extensometers or this other group called the Whittemore strain gauge, if I pronounce it correctly. So this is the other category. You directly measure the physical thing, right? Just by the displacement between these two jaws, something like a caliper, for instance, huh? Imagine a caliper is opening up and you're measuring that, or a micrometer, but way more sensitive, of course. Of course, probably not way more sensitive than a micrometer, but they should be sensitive enough because strains are typically small numbers, so they should be able to get small numbers. And there are some other categories that the change in the length is not necessarily leading to the change in resistor. Instead, it leads to the change in inductance. Now that L and this L are different. This is length, this is inductance, or the change in capacitance, or the change in a magnetic field or something. So the change in the length is affecting change in other electrical entities. So they could be inductive systems, they could be capacitative systems, or magneto-resistive strain gauges. And here is an example that I found online from a capacitative. So it is changing the capacitor because a capacitance of a capacitor, if you remember, it is also related to the distance between the plates. So if you had a capacitor like this, and it is filled with some material here, and then the distance between them is D, correct? And the area of these plates that are storing the electric charges is A. If you remember, the capacitance equals what? it is epsilon and then A over D, where epsilon is the permittivity, electrical permittivity of the material that you filled inside those two plates, between the two plates. So clearly, if you don't change that material or the plate, you see it's a function of distance. And if this distance is correlated to that change in the length, when this distance changes, the capacitance changes, and this can lead to changes in the voltage, which you can measure. So that's another way to do it. Or for a solenoid, you know that the inductance is it depends on the length of the solenoid. So you can clearly see that we can relate the change in the length to change in these different electrical measurements or electrical properties. Now, the electric strain gauge, the electric resistance strain gauge, is the most common one that, as I said, it has been around for about 100 years. You attach them to the parts by typically an adhesive, and when it deforms, the resistance of it would change, which is typically this change in resistance is measured using a circuit called Wheatstone bridge. And I'll show you what the Wheatstone bridge is. And there is something in a strain gauge called the gauge factor, using which we can determine this change in resistance. So first of all, what is this gauge factor and what is this Wheatstone bridge? So Wheatstone bridge is basically something like this, is an electric circuit that you measure change in electric resistance. It has three fixed resistors, R1, R2, and R1 and R3. These are fixed resistors. There is the unknown resistors, Rx, that you want to measure, and there is a variable resistors, R2. And here you have a voltmeter or an ammeter between these two ends of the bridge, D and B. Now, in general, if the voltage that you provide to the bridge is V of source, you can show that using the Kirchhoff's electric current and electric voltage laws, the first and second laws of Kirchhoff. You can show that the voltage through this bridge, dB, is equal to this formula. Okay, so if I can measure VG and I know Vs and I know the values of R1, R2, and R3, I should be able to measure the resistance. Now, what about Rx? We're going to talk about it. But what we typically do in this bridge, we change R2 such that the bridge becomes balanced. What does balance means? Means the current that is going, the voltage on this side and this side, they are the same. So the voltage of D and B are the same. So no current passes through VG. When no current passes through VG, then basically R1 and R2 are series, R3 and Rx are in series, and then the result of those two are in parallel. Now, when it's in balance, you can show that between R1, R2, R3, and Rx, this simple relation exists. So this R2 is the one that I change. R1 and R3 are fixed. So I change R2 until no current passes or no voltage passes between no voltage exists between D and B, or no current passes through it. And this is my unknown resistance that I can measure, correct? So this is the formula for Rx when the bridge is balanced. When the bridge is not balanced, which means Vg is not equal to 0, this is the formula between Vg and Vs, okay, where you see all the four resistors are in it. But if Vg is 0, it's balanced, you can see that these terms both go to 0, and then these two would cancel. So clearly Rx is R2 over R1, R3, which is exactly this guy here. So by changing this R2, I'm able to measure Rx. So the goal of it is to measure an unknown resistance, which is the resistance due to the change in the circuit. So this is your Rx. This is the one that will change. Initially, you might know it, but after it changes the length of it and it changes the value of it, you don't know it. But with Wheatstone bridge, you can measure that. And the good thing about Wheatstone bridge is it can do very accurate measurements. So the change in Rx also can be accurately measured. Now, if you do proper installation of these gauges and you use correct adhesive and correct gauge and everything, you can go very small and you can go as big as 10%. So epsilon as big as 0.1, which is a very large epsilon, you are able to measure with these. Now, exactly what formula would you use? The formula is based on this parameter called gauge factor. Gauge factor is the change in the resistance of that resistor divided by the original value of it divided by the strain. Okay, so if you know this gauge factor and you know the initial Rg, and you can measure this delta R through the Wheatstone bridge, then you should be able to find the strain, this epsilon here. Okay, now in terms of voltage, if you want to talk in terms of voltage, the excitation voltage of the bridge is EV and the output voltage is SV, the sensor voltage. Then these two voltages are related by the gauge factor and by the strain. So again, if I know how much voltage I gave to the system, how much voltage I got back, and I know the gauge factor, which depends on the physical properties of my gauge, then from here I should be able to easily calculate for the strain. Now, for typical metallic gauges, this is a little bit over 2. For semiconductor strain gauges, it can go very, very larger numbers like 50 or 200. And is that a good thing? Yes, it is, because you can see that when this number is very large, okay, that means this number can be very small. So basically, if this is very large, if I look at this formula here, you can see that epsilon is what? Is delta R over Rg divided by Gf. And when this Gf is very large, you can measure very small strains and you can measure it accurately. So it's always good to get a good gauge factor, a large gauge factor, and that is coming from the semiconductor with piezo resistive effects. So hopefully this brief introduction to strain gauges and measuring strain is useful to you. You learned some basic things about the strain gauges, different types of them, and the Wheatstone bridge. And I'll see you in the next video. Thank you.